Our next speaker is from Germany, Raik Brinkmann of OneSpin Solutions. Raik is co-founder of OneSpin Solutions, was named President and CEO in 2012, with overall responsibility for leading the company and its business growth worldwide. He brings to this role more than 15 years of broad experience in management, verification and industrial R&D, having served at companies in both Europe and the US. And the title of his talk is Qualification of Verification Environments Using Formal Techniques.
Thank you for the opportunity. Just a few words on OneSpin. Maybe you don't know us well yet. OneSpin's been around for quite a while, and we've been developing some unique formal technology in the coverage area lately, most notably the observation coverage analysis that we will focus on today a little bit, and also functional coverage aspects are targeted. We also look into sequential occurrence checking, especially for FPGA and ASIC synthesis flows, and have been investing a lot into usability features that allowed us to actually double our revenue last year and triple our bookings. And what we're doing in the next couple of months and years is keep moving the innovation forward. And we have done that specifically in the area of functional verification with assertion-based verification techniques, which range from automatic checks to coverage-driven property development. And that's what I want to show you a little bit. Following the following outline, I want to show you a little bit about how analyzing code reachability helps you improve your test benches, and then move it a little bit upwards by looking at state machines and trying to cover the state machine transitions, but also looking later into what actually the design is doing and connecting that with coverage techniques, both on the code side and also on the functional side, that close the picture of how we want to move the level of abstraction upwards a little bit on this verification scenarios. Now, we have already seen in the previous talks that verification environments are pretty much built the same way. You always have some kind of stimulus generation. Informally, you take constraints as a substitute for that, excluding unwanted scenarios. And then you have some sort of checkers that will either be simulation checkers or formal assertions. And you can ask yourself, can you activate actually the design? What's the reachability coverage there? And the other question is, how good are your checkers or assertions? So what's the observational power of your verification environment? Reachability coverage is pretty known, so you probably know that you can actually run a formal tool to check whether some code is reachable or statically unreachable. Usual formal verification tools will create assertions for that, a cover statement that will basically check whether something is dead in your design. And if it's not dead, you can create some code coverage example that shows you which part of your design is executed. In this case here, the red parts are executed, the blue parts are actually analyzed, and in this case, the expression would be false, so the white part is not executed, and then you'll jump into the else branch. So this is the basic picture that you get. Now, if you look at FSMs, finite state machines, it's pretty much the same thing. You can look at, is the finite state machine correctly reset? Is it unreachable, or any states unreachable, or are there deadlocks? What you want to do is you want to synthesize checkers again to cover the initialization, each state and each transition, and also the absence of deadlocks. That's pretty much standard. So I want to take an example and show you what else we can do there. In this case, an SD-ROM controller, just two sides and two interfaces and a few operations like reading and writing, pretty much standard. So what you can do with the formal tool is actually extract the structure of the finite state machines from the RTL automatically, and then run a formal analysis on the reachability of these transitions and states, and you can depict that in a matrix here, showing which state is reachable by which transition. Now, if you want to go a step further, because this is basically relating to code coverage in a sense, you can ask yourself, what are the actual transition passes through this transition graph? And in this case here, I can formally write a property that states if I'm in idle state and I'm going through the state SR1 and back to idle, how can that happen? And it will probably cover the red part in this graph here and in a more general way here. And the tool will actually give you a trace that says, okay, I'm in idle state and I'm going through SR1 and going back to idle. And what we observe here is that we are passing through row activation, and in this case 2 times. And the question is now, is that the general operation of the design, and can we prove that this is always happening? And of course we expect that this, as a designer, we know that this corresponds to a single read operation. Can we prove something about this instead of just looking at the coverage aspects here? And what we do is, if you look at coverage and look at transitions in the finite state machines, you will notice that there are some important states that you can clearly identify by looking at the diagram. This is row activation and idle in this case. And you can see that many transitions start and end there. So these are pretty interesting candidates for looking into more high-level operations of what the design is doing. Basic operations of my design are reset, pre-charging, row activation, reading and writing, and more complex would be burst reads and burst writes in this case. Then if I look at the more abstract way, the design looks like this. I have these operations that start in idle and go to row activation, and from row activation I can go to single write, burst read, and single reads. And what I want to do is I want to conceptualize this in abstracting away from the state machine and having this kind of abstracted picture, a graph that shows me what the design can do. And if I can capture all the operations in this conceptual state machines with assertions, I can basically have a much better coverage than looking only at the line coverage that I can achieve. So I want to do that with something that we call operational assertions, which are a simplified version of assertions that basically consists of a cause and effect relationship that is made up of something that causes an operation to actually happen and something that we want to observe, the proof part, and that will stretch over a certain number of time frames. So if you look at this on the timing relationship, then you see here how the single read operation would work. And the blue parts are basically corresponding to the causes. These are the things that I have to assert to make this single read operation happen. And the blue parts, red parts, I'm sorry, are the expected effects. If I make this a very simple assertion, and I can prove that from a row activation state and having a read request and no write request and no burst and so on, that I actually end up after 5 cycles in the row activation state and passing through these SR1 to 4 states all the time. So I can prove this. And that basically gives me already some indication of my design, how it works, and what must always happen. Now the question is, how much verification did I do here? I can take what we call observational coverage and measure automatically how much of our code has been actually observed. And what this means is, I show you in a simple example here. What we do is we want to insert arbitrary failures into the design and measure how much of our assertions or how many assertions and which assertions cover these actual behaviors. And in this case, what we do is we have a design in a very simple assertion, which only covers obviously a simple statement here. It's very simplistic, and what we want to do is we modify it by adding 3 inputs at each individual assignment here. And don't worry about the syntactic question of whether you can actually write that down. That's not necessary. We can actually put that into the model, into the formal model that we analyze, and thereby remove the restriction of the syntax here, in this case Verilog, to write things like that. What we then do is we actually check the assertion in principle on all these different modifications of the design and see that the assertion will fail only for one modification, and for the others it would still pass, and that's showing us that we never really looked at what's happening in these cases. So that's the basic principle. And if I apply that to my to a simple set of properties, I can come up with something like this picture. The green part shows, for example, here in the single read operation, that I actually verified that these state transitions must happen. So this is considered covered or observed. And the yellow parts are actually activated. However, they're not observed, they're not checked for, so we don't really know if this is something that we want to happen or whether this is something that shouldn't. And the red part actually shows things that are not activated in this case and that we must probably look at and write some more assertions. So what I'm trying to show you here is that if you apply this kind of coverage technology combined with a methodology to analyze your design, you can actually apply it in the very early stages of your design verification and get benefit for writing your first assertions here. You also can get some statistics on it to see which part of your design needs more improvement and where you want to look at. And if you look at a more complex way, then as I've shown you in a slide earlier, we have not covered particular outputs or particular transitions that happen here. That will give us indication of what else we have to specify in our case. So we would refine our assertion here in this case and talk about more behaviors on the outputs. If you do that, you can come up with an assertion here on the left that covers the complete read operation, and you can show here in a graphical way, in a waveform, how this operation can happen, how it works. Is this really functionally complete? So how do we know that we have done a good job on the functional side? You can argue that if you have covered, in a sense, all the design RTL with assertions or with tests, and everything is green, that you have done a good job on the functional side. However, it's not always the case that you get that kind of functional coverage, because you might have missed something that you have in the specification, you didn't actually implement it, or some things are contradictory, or other reasons that you have simply forgotten to consider some input scenarios. And what I can show you now is how that can be analyzed automatically. We can take this RTI code, and what we want to do is we want to prove that our set of assertions actually forms a reference model, a bisimulation model for our RTL, and that our assertions completely cover the functional space of the design. To do that, we need three criteria, basically: input coverage, output coverage, and sequence coverage. I don't want to explain everything in detail here because it's getting too far. Just one thing, one example. Suppose we have not written anything about our bursts. So all our operational assertions have some condition in the cause part that says we don't want bursts. Then we can take the following approach. We take a single operation, like a single read, and check each one that can follow, that starts in the same state, and ask, is all input behavior covered? And in this case, the tool will tell you, okay, suppose you have a single read operation that can also be visualized here. This goes from here to here on the right-hand side. And if I add the next transaction, like a single write operation or row activation or whatever, there's no case where we can find a matching assertion that will cover the case where the burst write is asserted. And this is depicted here. So you will actually get the trace from the tool that says, look, this is a trace where no assertion can follow, and you have found the functional verification hole. In general, the procedure that I've shown you would go starting by capturing the central control, like I did for the final state machine, capturing the full control of all operations, so actually trying to cover all operations that you have. Then adding more operations, so the second phase would be adding more outputs, so you basically cover the operational aspects of it, and then you will go for covering all operations, and finally maybe you want to do some more on extended functionality, so you can build it up. The general picture looks mainly like this. You have your test environment and your DUV. You run coverage analysis, and that gives you three different kinds of outputs. One is the control coverage or reachability coverage or activation coverage, whatever you want to call it. That's relevant for simulation as well as for formal environments. Also observation coverage that you can measure for simulation and verification, formal verification environments. is something you can compute automatically. What you also might want to do is tie it back into your verification plan with some functional coverage aspects, and that can all be working together as I've shown you here. And in essence, verification management is an important aspect. Leveraging functional specification details can drive the test plan and manage verification process. We can raise the level of abstraction for both the test bench and the coverage of functional aspects, and it's a critical and rigorous endeavor. So in essence, OneSpin is the company who's innovating in this area. We are promoting quantify coverage and operational assertion and so on to target these requirements. Thank you.